Hello everyone. So this is a continuation of my previous video. So in this video, I'll be solving problems of VTU Model Question Paper 2 of Basic Electrical Engineering, wherein I'm solving problems from Module 3 and Module 4. And Module 1 and Module 2 problems I've already solved in my previous video. So those who have not seen, I'll put the link in the description. So coming to problem 3, module 3, question number 5b, 6b are from module 3 and question number 7b and 8b are from module 4, which are problems. So let us see module 3, problem 5b. A shunt generator delivers a 50 kilowatt at 250 volt and 400 rpm. So, and the armature and field resistances, armature resistance is given as 0.02 ohm and field resistance RSH or shunt field resistance is given as 50 ohm. Calculate the speed of the machine running as a shunt motor taking the same power and the input at 250 volt. Allow 1 volt, it should be 1 volt per brush for contact drop. So your brush contact drop, since there are two brushes, it will be 2 volts. So the moment they give it as a shunt generator, it is always better to draw electrical equivalent diagram of a DC shunt generator. You can get an idea of all the formulas over here. So you have a shunt generator which is delivering to the load. So IA current will flow out of the generator, armature current. Now this will split up as ISH and IL. You have been given that the terminal voltage at the load side it is 250 volt and the power is 50 kilowatt power. So you have power as 50 kilowatt and voltage, terminal voltage as 250 volt. So from here directly you can calculate what is the load current IL. IL will be equal to now 50 kilowatt or 50,000 divided by 250. You are going to get the load current as 200 amperes. So now since the load is connected in parallel with the shunt field winding, I can also write ISH is equal to the shunt field current you do not know. You can calculate V divided by RSH because the voltage which is appearing across the shunt field winding is the terminal voltage V. So V is nothing but 250 divided by the shunt field resistance, that is 50. So you are going to get ISH as 5 amperes. So ISH is calculated, IL is calculated. Directly you can apply KCL at this node. So if you apply KCL at node X, you can calculate at node X. At node X, I can write IA is equal to IL plus ISH. So that implies IA is not known. So IA is equal to IL is nothing but 200 plus 5 ampere. So you are going to get it as 205 ampere as a armature current. So once you calculate the armature current, if you apply KVL over here, so if you are applying KVL, so if you are applying KVL to the outer loop over here, you can write the KVL equation as KVL equation as V is equal to, I can write it as EG minus IA RA minus BCD, that is a brush contact drop. That is what we can write, or EG minus V minus IARA minus BCD is equal to 0. So that is a KVL equation. So V is known, that is 250, that is equal to EG is the one which you need to calculate, minus IA. IA is armature current, that is what you have calculated as 205. RA is equal to 0.02 ohms minus 2. Now if you calculate, if you calculate this, you are going to get the value of EG as 256.1 volts. So once you calculate the value of EG, now we can see the question. They have told that calculate the speed of the machine running as a shunt motor. Now when the same machine is run as a shunt motor, when the same machine is run as motor, the generated EMF will be nothing but the back EMF of the motor. The generated EMF will be the back EMF at the armature, back EMF of the armature of motor. So your EB will be EB1 I can write it as 256.1 volts. Now running it, they have already given in the question as it is running at 400 rpm. So I can write N1 as 400 rpm. So first part of the question we have, first half of the problem we have solved, but again we need to calculate what is a calculate the speed of the machine when it is run as a shunt motor. Now when it is run as a shunt motor taking the same power, you draw when it is a case 2 a DC motor, when it is run as a DC motor, how does it look like? You have this again the armature, you have this armature, then it's a shunt motor, so field winding is connected in parallel with the armature. Then you have a voltage which is given, so that is same as 250 volt which is given. So the line current is flowing inside, and this will be the current will flow inside the shunt field winding, and armature current will flow inside this armature winding. Now you can write at KCL, if you name this node as Y, at node Y, you can write IL is equal to ISH plus IA. ISH is nothing but V by RSH. V is the same, that is 250, which is already given, and RSH also remains the same, that is 50. So the shunt current remains the same. Similarly, you can write IL. IL as nothing but the line current. Power is given, that is the same, 50,000 divided by 250. It is nothing but your 200 amperes. So IL you have calculated, ISH you have calculated. The next you need to calculate what is the armature current. Therefore, I'll directly shift over here. So armature current IA will now be equal to IL minus ISH. So that implies IL is nothing but 200 minus 5. So it is nothing but equal to 195 ampere. So once you have calculated this, what we have to do is we need to calculate again, apply KVL at the outer loop. So if you are applying KVL to the outer loop over here, you are getting the equation as V. You know that it is V minus KVL. If you are applying V minus EB, directly you're shifting over here. Okay, V minus EB minus IARA minus BCD is equal to 0. Brush contact drop. V you know it is 250 volt. EB you need to calculate. So minus EB minus IA. IA is 195. RA is 0.02 minus 2 is equal to 0. That implies EB is equal to your, if you calculate this, you are going to get it as 244.1 volts. So this is how you calculate the back EMF when it is run as motor. Now the last step is you need to calculate what is the speed when the machine is run as DC motor. So we'll solve over here the last step. So when the machine is run, you know that you know the formula EB2 by EB1 is equal to N2 by N1 in a case of shunt motor, because into phi1 by phi2. Now the component phi1 by phi2 remains constant, because if you see when the machine is run as a DC generator and motor, your shunt current remains the same or the flux remains the same. So your phi1 by phi2 is constant, right? So this can be neglected. So your EB2 is nothing but 244.1 divided by EB1. EB1 is nothing but 256. You have already calculated, that is a generated EMF, that is equal to N2 divided by N1 is nothing but 400 rpm, which is given in the question. Now that implies if you solve this, you are going to get the answer N2 as 381.257. 381.257 rpm. So if, or it is 381 rpm. So this is how you are going to solve this problem on a DC generator as well as DC motor. Coming to the next problem, that is 6b, which is again from the same module. So a 4-pole 500 volt shunt motor has 720 wave connected armature. So a 4-pole. So the question is already clear. P is equal to 4. 500 volt shunt motor. So V is equal to 500 volt shunt motor has 720 wave connected conductor. So Z is equal to 720. Wave connected, so number of parallel paths is equal to 2. The full load armature current is 60 ampere, so Ia is equal to 60 ampere, and flux per pole is 0.03 Weber. So the armature resistance Ra is equal to 0.2 ohm, and brush contact drop is 1 volt per brush. So since there are two brushes, you have 2 volt because it is 1 volt per brush. Calculate the full load speed of the motor. So it is a shunt motor which is already given. So you have a shunt motor, a field winding is connected in parallel. Then you have the voltage of 500 volts which is being applied, and IL, ISH, then Ia is flowing into the armature winding. Now to calculate the speed, I have the formula Eb is equal to 5ZNP by 60A. But to calculate speed, I already know 5Z as well as P and A, but I don't know Eb. To calculate Eb, I need to use this KVL equation to solve the given problem. You have V, so directly I can calculate ISH is equal to V divided by RSH. So V is nothing but 500. 500 divided by RSH is given. Armature resistance is given 0.2 ohm, or okay, so say it is not required, sorry. I can directly apply this KVL equation. So you can apply KVL to the outer loop. If you apply KVL to the outer loop, you can calculate, you can get V minus EB minus IARA, okay, minus BCD is equal to 0. So V is nothing but 500 volts which is given. So 500 minus EB minus IA. IA is 60 which is given. RA is 0.2 minus 2 is equal to 0. Now if you solve this, you are going to get EB as 486 volts. So once you calculate this EB, directly you can apply the formula of EB over here. So 486 is equal to 5 is 0.03, Z is 720, N is what you need to calculate, P is nothing but 4 divided by 60 into 2 since it is wave connected armature. So if you solve this, you are going to get the value of N as 675 rpm. So this is how you solve the given problem. Coming to the next problem, a three-phase 400 volt which is from module 4. So from module 4, we are solving the next problem. A three-phase 400 volt 50 hertz supply is given to a three-phase induction motor. So the supply voltage is 400 volt. So supply frequency is 50 hertz. And it's a 4-pole induction motor. So P is equal to 4, runs at 1440 rpm. So your N, speed of the rotor, is 1440 rpm. Determine the slip, it should be slip, and the frequency of the rotor current. So you need to calculate S, and frequency of the rotor current is F dash. Speed of the rotor is already given 1440, so the question is slightly wrong. You need to calculate the slip over here, and the frequency of the rotor current is F dash. So you can calculate first the synchronous speed of the motor. So Ns is equal to 120 F by P. So 120 into F is equal to 50 divided by P. So you are going to get this one as 1500 rpm, the synchronous speed. Once you get the synchronous speed, you can calculate the value of slip, Ns minus N divided by Ns into 100 in terms of percentage slip, what you're going to get. That implies it is 1500 minus 1440 divided by 1500 into 100. If you are going to do, you are going to get the percentage slip as 4%. So this is the answer for slip. Next you need to calculate F dash. You know that, we know that F dash by F is nothing but slip. That implies F dash is nothing but the frequency of the rotor current which you need to calculate. F is a supply frequency 50 Hertz. Slip you have already calculated 4% or 0.04. That implies you are going to get F dash as 2 hertz. So this is a frequency of the rotor current. So this is what is required to be calculated. A very simple problem, you can easily score marks. Coming to the next problem, that is 8b from module 4. So a 3-phase 16 pole alternator, so P is equal to 16, has a star connected winding with 144 slots and 10 conductors per slot. So you have 10 conductors per slot. The flux per pole is 0.03 Webers and the speed is 375 rpm. You need to calculate the frequency and the phase, that is EP is equal to question mark, EL is equal to question mark. So you know the formula to calculate the frequency. F is equal to NP divided by 120. N is 375 into 16 divided by 120. If you solve this, you are going to get the frequency as 50 hertz. So once you are doing this, next you see the formula. EP is equal to 4.44 F 5 T Kc Kd. So pitch factor and distribution factor. Frequency you have calculated, phi is known, but you need to calculate T. Then Kc, it is a sinusoidally distributed. Pitch factor is 1. So Kd you need to calculate. So first we will find what is T now. What is the total conductors? Total number of conductors Z, that is equal to 144 slots. So 144 slots into, in each slot there are 10 conductors for the complete machine. So there are 1440 conductors. Now since it is 3-phase, so Z per phase you need to calculate over here for a single phase. For each phase you need to calculate how many conductors are there. 1440 divided by 3, you are going to get as 480 conductors. Now T is nothing but number of turns of coil per phase. T, you know that it is Z divided by 2. Since I have already calculated Z per phase, please don't divide again, divided by 3. Z is 480 divided by 2. You are going to get it as 240. So T you have calculated. Now you need to calculate KD. KD is nothing but sine m beta by 2 divided by m sine beta divided by 2. Now where this is important, if in the problem it is not given, you need to calculate. So where m is number of slots per pole per phase and n or one beta is equal to 180 degree divided by n, where n is nothing but number of slots per pole. Number of slots per pole. Now with this we are calculating. So this is a formula to calculate the value of KD. So let us calculate what is the value of KD now. So KD, so before that we will calculate what is M. M is equal to number of slots, that is 144 per pole, so 16 per phase. So they have given it as 3-phase, so per phase. So 144 by 16 divided by 3. If you calculate, you are going to get the value of M as 3. 144 by 16 as 9. 9 by 3 is 3. So you are going to get M as 3. Now you need to calculate what is beta. Beta is nothing but 180 divided by N. So it is nothing but 180 divided by N is number of slots per pole. So 144 divided by 16. So 144 divided by 16 is 9. 180 by 9 is 20. So beta you have calculated and M you have calculated. Next you need to calculate what is KD. Therefore KD is equal to sine of 3 into 20 by 2 divided by M sine. M is 3 sine beta. Beta is 20 divided by 2. Now if you calculate this, you are going to get KD value as 0.9598. Roughly you can take it as 0.96 also. So KD you have got it as 0.9598 or 0.96. So with this you can calculate the phase EMF as 4, therefore 4.44. F is nothing but 50. Phi is already given in the question, that is 0.03. 0.03, F of 5T, T is 240, Kc is 1 and Kd is 0.9598 or it is 0.96 also. So if you do that, you are going to get EP as equal to 1534.1364 volts. So this is a value of phase voltage. Now line voltage is equal to, you know that it is root 3 times EP for a star connection. That implies EL equal to root 3 times 1534.1364 volts. So therefore EL will be equal to 2657.2022 volts. So this is a value of the line voltage what you are getting. So there is no problems in module 5 which is given in model question paper 2. So this ends all the problems from model question paper 2 of VTU model question papers. So thank you for watching my video. In case you find that this video is useful to you, please like, comment, as well as you can share it with your friends so that it can be useful for them for their studies. Thank you.